Okay, so this lecture is being recorded. Just so you guys know, we're going to get into series parallel resistive circuits. This is where you have to take and apply all of the information and knowledge that you've gained on series laws and parallel laws and figure out how on earth do they work together, right? And when do I apply which laws? Yeah, it can cause those. So what do you see here? What types of circuits do you see? Yeah, so there's both individual series circuits, there's both individual parallel circuits, and there are circuits that combine both series and parallel. So this is what we're going to get into and what they can really look like. We're going to identify the resistors that are in series in these circuits. We're going to identify which ones are in parallel. It's going to be fundamental because then we can calculate the resistance of those things in series and in parallel and put them together. Same thing with the current law and the voltage law. We'll be able to apply them appropriately in these circuits, and we're going to solve problems regarding these circuits. But to start with the basics, we start with what are the laws or formulas for series circuits? We know that our current in a series circuit is going to remain the same. We know that our voltage in a series circuit is going to be the sum of the volt drops, right? Our total voltage will be the sum of the volt drops. And we know that our total resistance is going to be the sum of the resistors, right, of each resistor. For parallel circuits, we understand that current is going to be equal to the sum of the current of each of the branch circuits, right? We know that our voltage is going to, our total voltage will equal the voltage across each one of those branch circuits. They're all going to be the same. And our resistance is that total resistance formula, or the reciprocal formula that we just learned about. This is how I write out my formulas when I was learning them, right? And I would write them out every time. And I would, here's my column, here's my column, here's my formulas, I'm good to go. This is what I would recommend you do once you sit your butt down for the exam, write these formulas down. When it comes to series parallel circuits, they have both aspects involved in the circuit. And you will find that in this particular circuit, R1 is in series with R2 and R3. R1 is not in series with just R2. That is very important to note. You will get questions on that, okay? R2 and 3 are in series with R4 and 5. Oh, that was supposed to be R5 and 6. That was a typo. R1 is in series with R4, okay? So you can see quickly here how if I asked you, is R4 in series with R6? What's the answer? No. It's in series with R5 and R6, okay? And that's something that you have to recognize right off the bat. When calculating the total resistance of a series parallel circuit, you have to add the resistive values that are only directly in parallel with each other. And then you add the values that are only directly in series with each other. And the reason why I have it laid out in these steps in this order is because if I find that if you try and do it any other way, mistakes are more likely to happen. Okay, so make sure that you add your parallel resistive values first with that total resistance formula for parallel, and then add your series values after to find a complete total resistive value, okay? Every time you combine resistive values together, redraw the circuit. It will help tremendously if you redraw the circuit. If you don't redraw the circuit, you might still get the right answer, and that's fine. But it is a detriment if you are struggling with these types of circuits and you don't redraw them. Okay, so it's just a step to help. Replace the group that was added together with one resistor and label it Rx. You can label it Ry, you can label it R whatever. I label it whatever the values are that it's replacing. So for example, in that previous circuit, we'll just bounce back. I would say when I combine R2 and 3, I label that R2, 3 as one resistor. And that way I know what previous resistors have gone into it. It just helps with my labeling. Always relabel and combine resistive values when redrawing the circuit. And essentially the goal is to break the circuit down and get one total resistive value. Your goal is to break that down to one series circuit, okay? And then use series laws to find things. Once the total resistance is known, you can apply Ohm's law to find the total current. And then you will build the circuit back up to find the voltage and current for each resistor. And it's just the way that you broke it down, you reverse that and build it back up. Yes, sounds good, Nathan. So we have Kirchhoff's current law. And as a review, in an electrical circuit, it is the sum of the currents entering a junction that must equal the sum of the currents leaving that junction. For Kirchhoff's voltage law, in a closed loop, the sum of the voltage rises is equal to the sum of the voltage drops. So, how is the size of a load in an electrical circuit determined? Well, if we have a large load, we'll have a small resistance and we'll draw more current. If we have a small load, we have a large resistance and it draws less current. So that nominal size of an electrical load is determined by the current it draws and not necessarily by the resistance that it has, okay? Although resistance clearly plays a factor into the amount of current that it will draw, when we talk about the nominal size, we'll talk about current draw. That's why we talk about plugs having 1 amp, you know, as we lay them out, or lights having, you know, 0.2 amps each, right? We don't say the resistance of the light is such and such. We talk about its current, just for you to be aware of. Let's get into some examples. So we've got 6 ohms on R1, 10 ohms on R2, 15 ohms on R3, 12 ohms R4, 6 ohms R5, 5 ohms R6, and 10 ohms R7. So what I want you to do is I want you to take the next 2 minutes and I want you to break this circuit down and build it back up to solve for total resistance and then the current values. The voltage that we will use here is 120 volts applied. Okay, let's get started. So for this circuit, what's the first step that you would do? Yeah, add resistors, what? 2 and 3, yeah. Yep, add resistors 2 and 3 and 5 and 6 to get R2, 3 and R5, 6, you betcha. So you get a resistance, R2, 3 is equal to 25 and R5, 6, 11. Okay, so now you redraw that circuit. Okay, you redraw it so that you've got your 3 resistors now. So it'll look something like this. Okay, so this is R2, 3. This is R4, and this is R5, 6. All right, then what do you do?
Find the total resistance for the parallel circuit, or parallel resistor.
Yeah, focus on this. Okay, so if I'm now focused on this, I use what formula?
Reciprocal.
Yeah, the reciprocal formula, you betcha. So then you focus on combining R2, 3, R4, and R5, 6 using the reciprocal formula. And what do you get for a total resistance? This is now R2 through 6. Okay, redrawing it, you should have 3 resistors in series now. R1, R2 through 6, and R7. And R2 through 6 is going to have a value of 4.67 ohms. Okay? We know that R1 is 6 ohms, and R7 is 10. Now we're going to find our R total. It's in series. So what do? Yeah. R total equals R1 plus R2 plus R3. Okay? So we just add those up. And you get 20.67 as your R total. Knowing that our E total is 120, we can now find our current, right? Use Ohm's law. I equal to E over R. These are all the totals. So then we go 120 divided by 20.67 ohms. And that gives you what? 5.8. So we know, redraw this real quick, that the current going through our massive 1 resistor is 5.8 amps. And we can redraw it like this. So we have 3 resistors now in series. And remember, the current didn't change in series, right? So this 5.8 is going to apply to each one of these resistors or groups of resistors. So then we go 5.8. I want to know what the voltage is here. My voltage of R1 is equal to my current of R1 times R1. So we got 5.8 times 6. We get a volt drop of 34 volts. Okay. We do the same thing here. Same formula. We get a volt drop of 27.1 volts. And the same thing here, and a volt drop of 58 volts. See how that works? Then we recognize that resistor 1 and resistor 7, we found everything for. We're done, those resistors. So now we just have to focus on this middle section. And how do we break this middle section apart? I'll erase some stuff there. So what I'm going to do is I'm actually going to stop sharing my screen for a second so you guys can see the board a little bit better, hopefully. hopefully. So then what we're going to do is we're going to take this middle group and now we're going to expand it out. And you expand it out the same way or in the same steps that you collapsed it, okay? Actually, that's going to be tiny for you guys. I'm going to redraw this so you guys can see it a little bit bigger. Okay, so that's our parallel circuit now. Remember, this is R23, R4, and R5, 6 that we got going on. We know that we have 27.1 volts. And we know, because this is parallel, that 27.1 is going to apply to each one of those branches, right? Then what we have to acknowledge is, okay, well, what is the ohmic value of R23? 25. It was 25. Can we find the current across or through that? You betcha. So our current is going to be equal to our voltage divided by our resistance, or 27.1 divided by 25. Okay? Then that would give us a current value of 1.08 volts. Volts? Nah, amps. Current's measured in amps. I love how all of you are just like staring at me. Like, what did he just say? We don't measure current in volts, we measure it in amps. Okay, so you got 1.08 amps. Make sure that you guys keep your numbers straight. And then we have R4. So R4 is going to be the same formula. I is equal to V divided by R. So 27.1 divided by the resistance across 4, which is 12 ohms. And that will give you a current value of 2.26 amps. And then you've got R5, 6. Okay, its total value was 11. So 27.1 divided by 11 gives you 2.46. Okay. Are we done? Say what now? Yeah, we're not quite done. We still have this branch and these two resistors, and this branch and those two resistors. So that's right. So we know that we have a current going through this branch of 2.46. We know that we have two resistors in here. And we know the individual resistance of each one of those. We know that R5 is equal to what? How many ohms? 6 ohms. R6, 5 ohms. So if we use Ohm's law again, we can say that our volt drop is going to be equal to our current times our resistance. So our volts of R5, current of R5, and R5. 2.46 times 6. What does that give us for a volt drop? 14.76 volts. And you do the same thing for R6. We've got 2.46 amps, and we've got a resistance of 5 ohms. That will give us a volt drop of 12.3 volts. You can also find this out by taking 27 and minusing 14.76. Should give you roughly the same number. Okay? So then we do the same process for this resistor up here, or this group of resistors. We've got 1.08 amps. We've got our R2 and our R3. R2 has how many ohms? 10 ohms. R3 is 15. So if we apply this same formula, we then will take 10, multiply it by 1.08, and get a volt drop of 10.8 volts. And we do the same here. 1.08 times 15 will give us a volt drop of 16.2 volts. Are we done? Nope, because that current going through this current here is the current through R2 and the current through R3. So we're done. If you follow those steps, you will be successful on these questions, right? Redraw and solve for those values. Okay, back to sharing. Oh, there's a question. The reciprocal formula is this one. Show you real quick. Go back in the slides. Whoop. Oh, didn't know I had to go back this far. There. It is this formula here. Okay. Jumping ahead. So here is another example. Given time, we're not going to go through the remaining examples. They are on the slides available for you to go through. And if you have any questions about them, please come to me and we can talk about them. Yeah, and there's all the answers for them, in case you're wondering. But in summary, when the voltage is the same across the loads and the currents add up, what type of circuit would that be? If the voltages are the same across the loads and the currents add up, what type of circuit is that? Nothing? I've put you all to sleep. Oh, there's a chat. There's someone in the chat. Parallel. You're right, Justin. Parallel. Voltages are the same. Currents are adding up. That's parallel. Okay. What is one way to identify that resistors are in series? Drawing a line. Is that what you I love it? Yes. No, you're not wrong. Not what I was thinking. But the current is the same. They all have the same value of current, right? What must be done to find the total resistance in a series parallel circuit? The process that we just did. Yeah, we break it down, okay, and redraw it a lot. Can you state Kirchhoff's current law? Anybody? No, roughly. Yeah, there you go. Good enough. Current in must equal current out. That is the most summative way to say it, John. Nice. All right. Well, let's go like this.